Hello friends, in this lecture we are going to look some more stuff about scalar vector and tensor perturbations. In the previous lectures we have seen that the perturbation to metric tensor is of this form. It has following components. This is 0, 0 component. This is 0i component, bi is 0i component, and then we have hij. Hij is a tensor, 3 by 3 tensor, which contains two parts. One is the trace part, which is in this part of the metric, and then there is traceless part, which is here. So looking at this perturbation in the metric tensor, we can see that there are two scalar fields here, A and scalar field D, which is contained in the trace of hij, and then there is vector field Bi, and Eij is the traceless part of hij. All of this we have seen in the previous lectures, and let us learn some more information about scalar, vector, and tensor perturbations in the metric tensor. So here is some brief information about scalar perturbations. Scalar perturbations, they grow in an expanding universe and they are responsible for structure formation. Vector perturbations decay in an expanding universe and they are of no interest in cosmology. Tensor perturbations are basically gravitational waves and they play a role in anisotropy of cosmic microwave background. So let's see how this course evolves. If I get time, I will talk about tensor perturbations. It's depending upon time and my priorities. But we will definitely look in detail about scalar perturbations in this course, which are responsible for the structure formation. Now, speaking of scalar perturbations, we have seen that A and D are scalars in the perturbed metric tensor Gij. But these are not the only two scalars present in the perturbed metric tensor. We can also extract one scalar from vector Bi, and we can also extract one more scalar from tensor Eij. So in this lecture, we are going to look at how a vector can be decomposed into another vector and a scalar, which means from this vector we can decompose it into two parts. One part contains scalar and one part will be vector. And this decomposition of a vector into another vector and another scalar is based upon Helmholtz decomposition, which you know from vector calculus. In this lecture, I would only mention the high level features of this decomposition, which are relevant for this course. But if your knowledge about this decomposition has become rusty and you want to know more about it, please go back to your notes from vector calculus, from your undergraduate course in vector calculus, and you have also seen a form of this in electrodynamics also. The very first course in I think it's third year physics course, undergraduate level in electrodynamics. There also you have seen decomposition of a vector into a scalar and a vector. So here I would just mention the highlights of this decomposition, and if I get time and based upon my priorities, I may do a video on this, a separate video on discussing all the basics of this decomposition, where it comes from. And if I do that, I will post the link in the description of this video. But for now, let us look at the highlights, the important points which are of interest to us. So a vector, any vector B can be decomposed into two parts. One part is we will call it BS. This part is curl free. This part is curl free part, which means its curl is 0, and this part is divergence free part. Its divergence is 0, and this curl free part can be written as gradient of a scalar field B, which is also called the potential of vector B. So this vector B, it has two potentials basically. One potential is the scalar potential, and when we say potential, we generally mean the scalar potential. And another potential is the vector potential, which is given by this part, But we are interested in the scalar potential here. We are interested in scalar field. So when we say potential, we mean the scalar potential. We are interested in this scalar field because scalar perturbations are important to us, at least in this course. Scalar perturbations are the main point of focus for us, because they are the ones which are responsible for the growth of structure in the universe. And yeah, so we need to extract a scalar by decomposing this B vector into BS vector and BV vector. BS vector is curl free, and BS vector can be written as minus gradient of a potential B. B is a scalar field. So do not confuse B with the magnitude of B here. B is not the magnitude of B, this vector B, but B is BS is a negative gradient of scalar field B. Now we will be using index notation a lot, because we are using tensors, and in tensors we write the physical quantities using indices. So let us see that how we can write this in the index notation. So we can write this B field as BI, and this can be written as BSI, BVI. These are all vectors in 3D Euclidean space. And next we want to write this constraint. I would call it constraint. That the constraint means the conditions that this vectors will follow. BV follow this constraint, and BS follows this constraint. So what is a constraint on BV? BV constraint is del dot BV is equal to 0, which in tensor notation or index notation, you can write it like this. So I hope that this is making sense. And if not, then I can quickly write down the steps here. So we have del dot BV is equal to 0. And what is BV? BV is equal to, let's say, or let me, yeah, you can say this is BV. This will be del BVX by del X plus del BVY by del Y plus del BVZ z by del z is equal to 0. In other words, you can say that the I component of this vector BV, the I component you differentiate by I, and this is 0. Now remember, we need to repeat over these indices, and if you want to write in proper tensor notation so that you don't forget to contract, so we need to repeat on this. So basically BV1 1 plus BV 2 plus BV 3 is 0. So that we in order to write it in proper tensor notation, we can write it as BV I J, and here I can say that I would like to contract this on J, and this will be I. Sorry, we can write it as like this, IJ. So we will contract both I's and J's. I will contract and J will contract, and this will become this. This is equal to 0. So the constraint del dot BV equal to 0 becomes this in index notation. Here. And this constraint BS is equal to minus del B. Sorry, this is not a constraint, but like writing BS in terms of B. So when you write BS in terms of B, this becomes BS vector is equal to minus B, a derivative of the partial derivative of B with respect to I. In other words, like you have B scalar is equal to minus del B, and this is BS I. Sorry. What am I doing? BS I component is equal to, and what is this? This is del B by partial derivative of the by x plus other components. So this is minus B I. This is how you write it in index notation. Okay, so from vector B, we have extracted scalar B, which is a function of x alpha for space-time coordinates. Eta is time coordinate, and this is x vector is 3D Euclidean space vector. So B is a function of all 4 space-time coordinates, just like other perturbations, they are functions of 4 space-time coordinates. So yeah, so we decomposed vector B into a scalar B and another vector BV. So yeah, so do we need to worry about this constraint? Because we have written this constraint in the index notation. Should we worry about this constraint also in the index notation? The answer is no, because now once we have extracted scalar B from this BS, we will not be writing our perturbations in terms of BS, but we will be writing perturbations in terms of scalar field B. So we don't need to worry about this constraint, but we will worry about this constraint. So now B has been decomposed into scalar field B and vector BV. And vector BV has this constraint del dot BV is equal to 0. Now likewise, we can do a similar decomposition on a tensor field. So what is the tensor field we are dealing with? we are dealing with this tensor field Eij, and you see that one decomposition has already been done the way we wrote this tensor field. The original tensor field is Hij, from which we already extracted one scalar d by decomposing this tensor into two parts. One part contains trace and another part is traceless. So one level of decomposition has already been done. But now this traceless tensor field, it can further be decomposed into a scalar, vector, and the remaining tensor. So let us see how we can do this. So we have a scalar, a tensor field, and this applies to any traceless tensor. What we are going to do here applies to any traceless tensor. So this is Eij. I want to extract a scalar from this, which means I want to decompose this Eij into three parts. From one part, I will extract scalar. From the second part, I will extract a vector. From the third part, I will extract a tensor. Now, this gives me scalar. This gives me vector. This gives me tensor. Now, think of a scalar. I want to call this scalar E. Okay. Now, I want to call this scalar E. And what are the conditions here on all these tensors? Note that this tensor is symmetric and traceless. Symmetric and traceless. So I want to apply all these conditions here also, so that if each individual tensor is symmetric and traceless, then this will also be symmetric and traceless. So because this left hand side is symmetric and traceless, I would like to keep all these three individual tensors symmetric and traceless. So each of this is symmetric. Each of this is symmetric and traceless. Okay. Now what next? So I want to extract a scalar from this Eijs. So this Eijs, I want to extract a scalar. Okay. I want to write this scalar in terms of E. So I write E. How to bring this Ij components here? Now you may this may sound like a hand wavy explanation, but I don't have any better explanation for you at the moment. But if you let your creativity run wild here, think of a mechanism by which you can get a scalar E and two indices Ij at the bottom. That's what we want to achieve, and we want to get and we want to keep these properties symmetric and traceless. So I have a scalar E, and I want to bring these two indices down here. So and I don't want to turn this E into a tensor, not into a vector, but would like to keep it as scalar. So one way, and I don't think of any other way, maybe there are more ways also, but a quick and easy way would be to do something like this. So again, this may not be convincing enough why we are doing it like this, but this, if you look at this equation, it gives me scalar E, and it is a tensor of rank 02, just like left hand side is rank 02 tensor. So this gives me a scalar E, and this is a tensor of rank 02. And what else? Is it symmetric? Think about it. If this is symmetric and then this is also symmetric, that means if Eijs is equal to Ejis, right? Oh, okay. Yeah, left hand side is symmetric, that we know. Now, is it symmetric? That means is Eij equal to Eji? Yes, because the order of derivatives does not matter. Whether you are writing like this or this, it is the same. Order of derivatives doesn't matter. So yes, this is symmetric also. And okay, this is symmetric also. And but yeah, the next question is it traceless? Is it traceless? No, we cannot say that E like 1 1 plus 2 2 plus 3 3 is 0. No, we cannot guarantee that. No guarantee here. So we want to make it, we want to make this traceless. So in order to make this traceless, what we can do is we can subtract the trace of this from this tensor. So far we have achieved one part of this, that we have constructed a tensor which is symmetric. But now let us subtract trace of this. And then this will be symmetric and traceless. So what is the trace of Eij? Trace of Eij, this trace is, this is equal to this, and this becomes, I can say, delta K L E K L, like this. Can I say it like this? Now it will contract on K, contract on L. Yeah. So this is the trace. Yeah. So I think this I need to correct. This is not subtracting trace of Eij, but this is I need to construct a matrix here which contains the trace. So this is basically tensor containing trace. I think that statement was misleading, that you subtract trace. No, you are not subtracting trace, but you are subtracting a tensor which contains trace. So I have that trace here. Let me say that, yeah, so this is trace. Let me call it TR. TR is trace. So what I need to do is that from Eij, I need to subtract trace by 3, trace by 3, and trace by 3, like this. So this matrix I need to subtract from Eij matrix, from this matrix. So what is this? In tensor form, this is, you can say, trace by 3 and delta Ij and trace divided by 3. So whatever this matrix is, let me say this matrix is like Xij. Xij matrix is delta Ij, delta KL, E, KL. So I have constructed Eij scalar to be equal to Eij minus trace, which is this trace by 3, trace by 3, trace by 3. Here it should be 3 minus 1 by 3 delta Ij delta KL EKL. Delta Ij delta KL EKL. So this is the sorry, did I make a mistake here? Yeah, so this is KL. So this EIJS, from this EIJS, I have extracted a scalar E. So EIJS is equal to scalar E, and this is scalar E. Scalar E. So from this EIJS, I have extracted a scalar E, which is a function of X alpha. Okay, now my next task is to extract a vector from EIJV. From EIJV, I want to extract a vector. I want to extract a vector. Now think of a vector. Again, is it based upon your imagination running wild, or there is some set logic to drive this? At this point, I would say that we have to construct it based upon our judgment here, our hindsight here, our intuition here, and somebody did it. It is not my hindsight. I have studied it from the textbooks, but somebody did it. What was the rationale behind that? At this point, I would only say that that this is one cleaner way of extracting a vector from EIJV. Is there any other way? I don't know. So let us look at the way which we know, which somebody did it maybe for the first time, and now we are using it. So that way is that I can write this as I want to extract a vector EI. So I need this EI vector. But here I have EIJ. So how can I bring J here? I can bring J down here by writing like this. So if I write this in terms of this EI, then this is one way that I write EIJ in terms of EI comma J. Then I am extracting a vector EI. But now I want to retain the properties of EIJV, that this is symmetric and traceless. So I want to make it symmetric and traceless, which means under the symmetric means under the exchange of I and J, interchange of I and J, the metric should not change, the tensor should not change. But right now in this state, if I flip IJ, it will change. However, if I add EJ I to this, now you see this will not change. Now if I flip I and J, this is, now it is same. Previously it was not same, but now it is same. So if you flip, now EIJV is same as EJIV. So now it is symmetric. Okay, so I have constructed a symmetric tensor by doing this. And again, this factor half is why do we have a factor half here? It is purely, I think, to retain some symmetry, because we have two vectors here and we want to divide by 2, and probably a mathematical convenience down the road when we plug it into equations. So we want to have a factor of 1 by 2, but whether you put 1 by 2 here, or you don't put any constant here, or you put any constant ABC, but this thing makes by doing this thing, adding these two tensors, we have achieved the property, the symmetric property of this tensor. Now the next property that we want to achieve from here is traceless. So is this vector a traceless vector? That is what we want to see now. Now, before we talk about traceless, we don't want this vector to contribute to give us any scalar component, because the scalar part we have already extracted from here. We have already extracted scalar part from here. So from here we don't want any scalar part. So what does that mean? That means this EI vector, if I were to write this as vector E, this EI vector should not give me scalar part, which means that if I were to write it as how should I say this, as E scalar plus E vector, if I were to decompose it into E scalar and E vector, and then I take divergence. What is E scalar? E scalar contains E scalar is minus del of some potential. This is some potential. What do you want me to write here? I can write here E, maybe. Don't confuse this with the scalar E which we saw before. This is just a temporary some explanation I'm going to give you for putting some constraint here in order to make this traceless. Now E is ES plus EV, decomposing E into two vectors, and let me call it E1 because we have already used E for scalar. So this is minus del E1 plus now I don't want to extract any scalar from here because I have already extracted scalar from the scalar part. This should not give me any scalar. So I want this to be 0, this part to be 0, this part to be 0, so that it does not give me any scalar because I have already extracted scalar from Eij. So I now only want to get to give me this vector part only. That means I want, going back to the Helmholtz theorem, which we saw in the beginning of the lecture, this is divergence free. This is divergence free. So I have a constraint here that del dot EV should be 0. Basically, EV is same as E here. So EI is basically EVI. It is EI is the, if you decompose E into curl free, this is curl free, which gives me scalar part, and divergence free, this is divergence free, which gives me vector part. There is no curl free part here because the scalar is already extracted from the other component. There is only the divergence free part here. So basically this is vector EI is divergence free. So this is divergence free. Del dot EV is equal to 0. So I need to, I have this del dot vector E. E is a vector which is extracted from, in index notation, this is EI. EI is a vector which is extracted from here, Eij, V part of the tensor. So del dot E is 0. Now I need to write this in index notation. Index notation, this becomes del dot E is 0. That means E I J del this delta ij, and contract on I, contract on j, this becomes 0. Now, what does this mean? This means that I have E11, 1, 1, E2, 2 plus E3, 3 is equal to 0. So what is this? This is the trace of Eij. Therefore, where is that? Yeah. So therefore, Eij is traceless. Ei, j is traceless. Traceless. So if Ei, j is traceless, then Ei, j plus Ej, I is also traceless. Then this is also traceless. Therefore, Eij vector part is this Ei, j plus Ej, I, and this is symmetric and traceless. Symmetric and traceless. So we have looked at two parts, scalar part and vector part. So what is the scalar part? So from here, we have seen two parts, scalar and vector. So what is the scalar part? Scalar part is this. Scalar part is scalar part is I hope this is right, but we can double check. Yeah, E minus 1 by 3 delta Ij delta KL EKL. Yeah, this is right. Yeah, this is right. And the vector part is half Ei, j plus Ej, I. This is symmetric and traceless by construction. This is the way we have constructed it, and this is symmetric by construction. This one is symmetric and traceless by construction. This is symmetric by construction and traceless by constraint, by the constraint delta dot E is 0, and which gives us E I comma j delta Ij is equal to 0. Because of this constraint, this becomes traceless. So we figured out scalar, we figured out vector. Now we need to figure out the tensor part. What is EIJT? We want this EIJT to be symmetric and traceless. EIJT is EIJ minus EIJ scalar plus EIJ vector. Simple. This is EIJT. Now this has to be this is symmetric and traceless. Why this is symmetric and traceless? Because this is S and T, this is S and T, this is S and T. So the whole matrix is symmetric and traceless. Okay, so if the whole matrix is symmetric and traceless, is there any other constraint that we can apply on this matrix? If this matrix is symmetric and traceless, that means one constraint is symmetric part. Yeah, so one constraint is on ETIJ is that this is traceless, and the traceless gives us one constraint from traceless. Constraint from traceless condition is that delta I j E T I j is 0, right? Yeah, this is 0. This is a constraint from traceless. Let me double check. I think this is right. Should be right. Yeah, this is 0. Now the second constraint is this constraint, which makes this transverse. That second constraint makes it transverse. ET ij comma k and delta I k is equal to 0. Now this makes it transverse. What do we mean by transverse? This transverse constraint is imposed here. We do not have it here by construction or from the initial requirements, but now we are going to impose this constraint. Why we are going to impose this constraint? Because in general relativity perturbation, we have seen there are gravitational waves. There are components in the perturbation which gives us which lead to gravitational waves. We want that gravitational waves now we want in the expanding universe. In order to achieve those in order to get the components of gravitational waves in expanding universe, we need this constraint. And we will look when we use all of these constraints in the Fourier space. When we look at all of these constraints in the Fourier space, then we will see that they would lead to the components, they would lead to the tensor modes which lead to gravitational waves. And we will see that when we will look at components in the perturbations in the Fourier space. And then this condition will be justified. Okay, so what next for today's lecture? We have seen that let's go back to our perturbation. Where is the perturbation? Here. So we have seen that this is the perturbation to the perturbations in the metric tensor A, B, I, H, I, J. So we have A, B, I, H, I, J. From H, I, J we have minus 2D minus 2D delta ij plus 2 eij, and From bi we get one scalar b, and then we get remaining part of the vector, which is bvi. From here eij we get one scalar e, we get one vector ei, and we get the remaining part of the tensor eij t. Okay, and on this bvi we have a constraint. The constraint is that divergence of this bvi is 0, which means we want its divergence 0. That means this bvij is 0, and we want this divergence to be 0. Delta ij ei j is equal to 0. This is one constraint. This is second constraint. Third constraint is that on this etij, third constraint is that on this etij it is traceless. This is third constraint. Am I getting the constraints right? Let me double check here. So we have yeah, this constraint here, delta ij, and delta ij here. Perfect. And yeah, and then we have the fourth constraint is this one, which makes it transverse. This one makes it traceless, and the fourth constraint, which we saw here, makes it transverse. Delta I k et I j k is equal to 0. Is this correct? Yeah, I k I j k is 0. Okay, this makes it transverse. So based upon these constraints, how many independent components do we have? How many independent components do we have for this perturbation in the metric tensor? Okay, so we have scalars. Let's list all the scalars: a, b, d, e. So we have 4 scalars, vectors. Let's go to the next page. Scalars have a, b, d, e. 4 vectors. We have b. After extracting scalar b, this is the leftover part, and then we extract one from tensor eij, which is ei, and then we have tensor, the leftover tensor after extracting scalar and vector. This is the leftover part of tensor etij. So there are 4 scalars. 4 scalars. So here we have 3 plus 3 components of this and 3 components of this. And here we have how many components? There are how many components here? So here we have, if you list all the components, you have total components is like this goes from 1 to 3, this goes from 1 to 3. So this is total 9, but 9 are not independent because it is symmetric. So because of its symmetric nature, we have 1 here two component here, third component here, second here, third here, fourth component is here, fifth component is here, sixth component is here, and sixth component is here. Because of its symmetric nature, there are total 6 components here. Now let us impose the constraints. When we apply the constraints, there is one constraint here that its divergence is 0. Because its divergence is 0, components of BV vector, they follow this constraint, divergence of BV 0, BV is 0. So the components follow this constraint that B1, 1 plus B2, 2 plus B3, 3 is 0. Now when you apply this constraint, that means the number of independent components reduce from 3 to 2. This becomes 2. Similarly, divergence of this is also 0. So this becomes from 3 to 2. Now we have total 4 vector components. 4 here and 4 now here. Now let us see that what we can, after applying constraints, how many components we have here for the tensor. We have, without applying constraints, we have 6 components. So these are the component numbers, not the values. So we have 6 components here, 1, 2, 3, 2, and sum of this is 0. So that is constraint, first constraint on this, that this is 0. So one constraint is that this is 0. So ETIJ constraints, that we have ET11, ET11 plus ET22 plus ET33 equals to 0, and that is constraint 1. What other constraint we have? We have constraint this thing, delta IK ET IJ comma K is 0. Now this gives me how many constraints? For each I, this gives me ET I. Okay, sorry, yeah, you can, yeah, basically this is same as I can put JK here because this is symmetric. So I can write this as, instead of writing IJ, I can write this as JI, same as JI. And then I contract on I and K. So when I contract on I and K, I can write this as ET J and if I were to contract on I and K, 1, 1, right? So plus ETJ 2, 2 plus ETJ 3, 3 is equal to 0, right? So how many constraints we have? Since J is from 1 to 3, so there are 3 constraints. This is total 3 constraints here. There are 3 equations I will get. So 3 constraints I get from here. So this would reduce this 6 components to how many components? One constraint is from the traceless. Traceless gives me 1 constraint. This gives me 3 constraints. So there are total 4 constraints. So that means this will reduce to 2. So degrees of freedom will reduce from 6 to 2 because of the 4 constraints. 1 constraint is this. 3 constraints are this. Because this J goes from 1 to 3. So I have 3 equations here. So 1 equation here from traceless, 3 equations from here, from this list of equations. And 1 plus 3, 4 constraints. When from this 6 I subtract 4, I will get 2 degrees of freedom. So how many independent components are there? I have, after applying all the constraints, I have 4 scalars, 4 vectors, and 2 independent tensors, 10 independent components. Now, when we look at this in Fourier space, when we apply gauge transformation later in the Fourier space, when we apply gauge transformation, transformations, we will see that out of these 4 plus 4 plus 2, scalar 2 can be set to 0 in the gauge transformation. So scalar will be reduced to 2. 2 vectors can be set to 0 in the gauge transformation. Vectors will be reduced to 2 and tensors are 2. So there are total 6 independent components, which we will learn when we do gauge transformation in Fourier space. So there are 6 real physical degrees of freedom and 4 are gauge freedom. 4 are gauge degrees of freedom, which means they can be eliminated. Gauge degrees of freedom, they can be eliminated by a proper choice of gauge. So by a proper choice of gauge, you can eliminate 4 degrees of freedom, you can eliminate 2 scalars, you can eliminate 2 vectors, and you will be left with 6. So those 4 are because the other 4 are present because of your choice of gauge. They are not real. And if you choose your gauge properly, you can get rid of them. Okay, that's it for today. Thank you for watching. It is becoming more and more interesting. Look forward to having more fun in next lectures. Take care. Bye-bye.